Okay. So.
Whenever you want, Matteo.
What?
Whenever you want.
Yes, I'm ready. So, first of all.
Wait, can I add one thing?
Yes.
Just to be sure everyone has it. So there is a link to the theory. And now I share the link. I put on Zoom, so everyone should have it. Right here. This is the copy of the presentation where you can find the theory about the designer experiment.
Yes. Also, let's say that you had problem with the creation of the project, or it doesn't work. You can also import an already created Cantilever Beam example, and you do this by doing File, New, Tutorial, and then you press Next. And you just select http.cossan.co.uk, and then from here you can get pre-made tutorials. So you can select Cantilever Beam, and if I press Finish now, it will import a pre-made tutorial with this exactly the same model. Okay, so in case you had some problem in the implementation, because now for the next step we need to start from what we have already. That is a finished and working model, actually the quantification model for the Cantilever Beam. Okay, so I closed everything and kept only the model page. So we want now to see at other type of analysis that are still related to to the design of experiment. You see my video, everybody? Okay.
Yep.
So let's as you saw before, we press the small play button, and we keep selected design of experiment. Now you can also change the analysis name, but for the moment we keep it as it is. We press next before we just stop the deterministic analysis. Now we can go to the next step, that is the design of experiment. And you can see that a new menu appears. These are various type of design of experiments, and you will find in the theory what they do. But two-level factorial is just combining minimum, maximum, all the variables together. Full factorial, you would say how many, which input you want to include into the design of experiment, and how many levels you want to input for them. When it's there are non-variables that are unlimited, unbounded, they will put like the mean, then plus minus 1 sigma, plus minus 2 sigma, and so on. Box Bankian is something similar, but it combines the inputs in a different way. Composite design, it's again combining minimum and maximum, but in hypercube fashion, or the possible combination, and then user defined, you just pass which value you want to evaluate. So let's start with the first one. Actually, let's start with full factorial. So how do we do the analysis? So we say full factorial, and we select all the variables that can be changed. So of course, you can only change variables that are the fixed variable that they cannot be changed in a design of experiment. Only the variable quantities can be changed. So in this case, that's why we are only seeing the random variables. We select all of them with shift click, and then we press OK. And you can see that it's saying how many levels we want to have for each variables. And let's put, for example, 3 levels for each variable. So this will be 3 times 3 times 3 times 3 analysis. And press finish. Now, if we go to see UQ model results and then engine output, again simulation data, you can see that it's exactly 81 analysis, because it's 3 to the power of 4, because we are doing three points for each variable and doing all the possible combination of these 3 points of all the variables. What can we do with these results? Well, what I suggest is that we can, you see that in this side, there are not only engine outputs, but there is also a folder. What is the difference between the two? Engine output collect all the outputs that are coming from OpenCossan inside Cossan-X, depending on which analysis you're doing. What does it mean? That in this case, we are just doing a design of experiment, so it's just containing the object that has all the simulation data object. That is the object that contains all the input and output values that has been used in the analysis. In next steps, when we start doing probability of failure estimation, we will have, in addition to the simulation data, we will have also object like a probability of failure object. Or if you want to do an optimization, if we do an optimization, you will see also an optimum object and so on. When you are from this view, you have access only to open in table view. If I click on open in table view, we close the previous one, you will see that we have all the 81 values of the inputs with all the corresponding value of the output. Now that we have more quantities, I want to show you something maybe more useful, how to export this data to a CSV file. So once you have the table view, you click on this icon here, that is next to the pattern, and you see it says export as CSV. So if I now click here, it tells me CSV files. So I say browse, and I will put, for example, a file in my desktop. And I will name export full factorial. We keep it .csv, and then we can keep you can semicolon or comma. Let's put it into comma, and then press finish. And now, if I go to my desktop, you cannot see because this is my second desktop, but I will move it very soon from the first desktop here, and you can see we have this export full factorial.csv. And if I want, I can open this into Excel. And this was regarding the question that we got before. How do we get the quantities from Cossan to Excel? It's like this. Now, let's go back to the GUI. As I said, this is just an overview of your simulation data, but maybe we want to have more detailed plots. Well, for this, we go to the folder containing the actual simulation data. This is the actual data that has been saved and is available here. So if I double click on this, I get an overview of what is inside. And you can see that I'm now looking inside the simulation database. From here, I was just getting an overview. So this is just an overview saying what are the variables and how many realizations we have and so on. And here we are actually looking inside. Now, these things you can also open it from MATLAB if you want, because this is actually reading inside a MATLAB file. But the nice thing is if I select, for example, E, I can get all the values of the sampled. This is, you see, is the classic MATLAB display output. These are all the values of the full factorial analysis, and in fact, they are repeated every free. They are repeated. Same for P or rho and so on. But the nice thing, it is much more interesting, is that now I can select multiple of the outputs and multiple inputs. For example, if I want to see what is the relation between Young's modulus and displacement in a kind of scatter plot, I can select E, and then with control I select W, and then you can say open scatter view. Now in this case, they are both at the same time showed as two series of data, but I want to create the relation between the two. So I click on this X stuff, it says set variable for X axis, and I select E. So we put like on the X, the Young's modulus, and on the Y, the displacement. And this is the three values that are being used in the design of experiments, and all the possible values, because we have all the variation of the other variables as well. Even more meaningful when we have this kind of design of experiment is to do a parallel coordinate plot. So let's select all the random quantities that I want to remember you are E, P, rho, and B, and the output is W. So we select E, P, rho, and no, wait, it was B or H random? Wait a second. Sorry, H is random. So let's select then E, P, H, and rho, and then W is the output. And then we click Open Parallel Coordinate View. This is showing all the possible combinations that we have done with this. You can see that it's just 3 points for each of them, and they are doing all the possible combinations. So from the 3 points, we get then 81 output. But the good thing, we can start limiting. So for example, we want to see what happens to the W when we keep, I don't know, H at the minimum and rho at the maximum. And this is showing, for example, these are the 9 outputs when we keep H to the minimum value and rho at the maximum value. In a similar way, you can play around and you can limit yourself, for example, to the middle or make high and high. And you can also reduce other variables and see what happens. So it gives us an insight of the functional dependency between the quantity. Now, in this case, it's just design of experiment, but you can see that when this is going to be completely random, it can also give us more information. Now, let's try to see another type of design of experiment. So let's go back to the model. Press play. We keep design of experiment, and we select now box banking. This is just fixed point, so we cannot put any parameter. We can only change if you want performance parameters, because maybe we are interested in smaller variation. So now, by default, it's getting the mean plus minus one sigma. So 1 plus minus 1 standard deviation, you can put 0.5, and then maybe only half a sigma, or stuff like this, or 2 if you want 2 sigma. And now let's go back to the results. So for this box banking analysis, we did now 25 analyses. And if we look at the parallel plot as before, you can see now they are not anymore easy combinations before, but there is more variation because it's a different set of data that is checked, but you can read it from the theory. And again, you can play around with the range of the variables to have an idea of what is their effect over the output. Okay. Now, this concludes the part on the parallel plot. On the parallel plot and the design of experiment. Should we go to the random part?
Yeah, please show the quasi-Monte Carlo simulation first.
Don't you want to show the theory first?
Well, no, because of the theory, basically, they can follow by themselves.
Okay.
So they are already pre-recorded videos.
Okay. So let me close everything again. And let's keep open only the model. And let me also close up these plots. Any questions so far, guys?
Are you able to follow?
Can you give me a feedback at least? Like clicking yes, clicking no. Unmuting yourself and then speak to us, say yes, all is clear. Because we cannot even know if you are actually here.
Come on, yeah.
Yeah, we're following you.
Okay, perfect.
Good. Yeah. Most of the people are still around. That's good.
Good.
Yeah, I suggest we can move to the design experiment using quasi-Monte Carlo simulation, because that's linked with Monte Carlo.
Also Monte Carlo. I mean.
Yeah, absolutely.
So, so far, what is the difference between the design of experiment and the Monte Carlo analysis? In the design of experiment, we are only evaluating some fixed deterministic points that are created with fixed deterministic rules. When you do uncertain quantification, it might be more meaningful to actually let the randomness evolve as it should evolve. That means completely random or quasi-completely random. That means going in a second type of analysis that is not anymore the deterministic part, but it's going to be the uncertain quantification part. So if we go to again to our play button, instead of selecting design of experiment, we can select uncertainty quantification. And then pressing next, we select simulation. The spam will probably be removed. It was an old feature that is not, it's supported only for finite element and we don't use it anymore. So it is just a temporary page, so just press next. And here we have access to the simulation methods that are for uncertain quantification. So we have access to 5 algorithms here. First is Monte Carlo, that is just the standard Monte Carlo samples, generating random values of the random variables according to their distribution with inverse CDF. Important sampling, you can change your distributions from starting from the original one to some other distribution that's mainly used for reliability. Sobol sampling and Halton sampling, here we are actually cheating because Sobol sampling and Halton sampling are actually not random sequences. They are purely deterministic sequences, but they are purely deterministic sequences that show characteristics very similar to randomness. And they are usually used to have a quasi-random design of experiments that gives a better coverage of the input space, especially when compared with standard Monte Carlo. Because when everything is really random, the points, especially when you have high number of dimensions and low number of samples, your points will not be covering in an uniform way the input space, but they will cover the input space in a random way. So for example, you will have some spurious correlation, spurious areas of samples, and so on. Halton sampling and Sobol sampling, since they are deterministic, they will cover the input space in a nice homogeneous way, much better than Monte Carlo when you are at low number of samples and high number of dimensions. In a similar way, Latin hypercube, Latin hypercube is a halfway between Monte Carlo and Sobol. That means that it's not completely deterministic, but also not completely random. Because what Latin hypercube does is that it divides the input space in as many uniform pieces as the number of samples. And then when you generate one point in a one regional space, that regional space is bound to get any other random point. So let's start with standard Monte Carlo. How do we do? Well, we just say standard keeps Monte Carlo selected, and we just select, we just say the total number of samples. Now, let's have a look on this window here. What is the meaning of this window? When we do Monte Carlo analysis, we can do multiple criteria for determination of the analysis. Some of them can be used only when you do probability of failure. Other can be done also when you do uncertain quantification. So coefficient of variation is used only when you do probability of failure estimation. So we will not touch it at the moment. But that means that you can do an analysis and say to the program, interrupt the analysis when my estimation of the probability of failure is smaller than a certain limit. Other way is run the analysis, do as many samples and run the analysis for some seconds, or do the total number of, interrupt the analysis with the total number of samples. Now, what is batches is we sample per batch. Batches is what is used to actually check the additional termination criteria, because the basic termination criteria is just stop the analysis when you reach a certain number of samples. For example, 1,000. And this is done by setting the total number of samples. And automatically it's up, sorry, wrong. 1,000 here. And you see that you can change sample per batch and batches, right? Now, what are batches used? Batches are used to check the additional termination criteria, because analysis, for example, if we check for the coefficient of variation, the analysis will do one batch, estimate the coefficient of variation, and then check whether or not the termination criteria is satisfied. If it's not satisfied, we'll go for the next batch, and so on and so on. Same for the execution time. At the end of the first batch, we'll say, am I exceeded my execution time or not? If yes, it will interrupt analysis. At the moment, we just care about doing 1,000 samples, so we just keep 1,000 samples per batch with one batch, and we get 1,000 total samples. And when we are done, we just press finish. Analysis was already executed, and if we go, now you see that the results, instead of being in design over experiment, appeared in uncertainty modification, because this was an uncertainty modification analysis. And if we look at the results, it's still the same structure as before. The simulation data is telling us that we have done 1,000 samples, and this was a Monte Carlo analysis. Again, we can, if we want, export as a table and so on. But let's go inside the simulation data in the folder. And let's select, as we done before, for example, a scatter plot of E versus W. So we select E and W, and then scatter view. As you can see, there is many more samples now. And again, we can select the x-axis, that is E. And this is a very nice scatter plot showing us what is the relation between the Young's modulus and the tip displacement. What we can see already, we can start getting some conclusion. For example, we can say that when we increase the Young's modulus, we decrease the tip displacement. Does this make sense? Well, yes, of course, because a higher Young's modulus means that the structure is more stiff. That means that the same, when we apply a same load, a more stiff structure will deflect less. Let's try another scatter plot. For example, P and W. Now we select as x-axis P. And this is showing that even if it's less remarkable than before, we can still see that there is a kind of positive connection. That means that when we increase the displacement, when we increase the load, we increase the displacement. It makes sense. When we apply more load to the structure will deform much more. Other type of plot you can get, for example, we can get, select only W and click on histogram. This is showing us the histogram of the displacement. And you can see, for example, that on average, the displacement is around, is not too far off the nominal displacement. If you remember, the nominal displacement was 7.2 millimeter. That means more or less here. And you see that it's very close to the maximum of the distribution of the output. And you can see the distribution of the output is not Gaussian, but has a longer tail on the high displacement part. Keep in mind this plot, because we will use it in the next analysis for the reliability part, because we will put some criteria based on the shape of this histogram. Other type of plot you can get. For example, you can get box and whisker chart. So let's select all the random variables and W. Oh, sorry, no, let's not select E, because E is a completely different dimension, because this is dimensional. So let's select, for example, H and W. And this is showing the mean, the median, sorry, not the mean, then the quantiles, and if there are some outliers and so on. But you will get some of this information also in the theory part. Other type of plot you can get. You can also get actually a plot of the series of all the samples that we got. So in line chart, these are all the outputs for every analysis. On the x-axis is the number of simulation. And the y-axis is the corresponding displacement for that simulation. So like this, you can see, for example, that if you look at 0, 0.011, that means 11 millimeters. You see that, for example, these samples are over the limit, right? And you can see how many out of 1,000 are over a certain value that you can imagine as a limit. Let me close everything now. I want to show now other uncertain quantification algorithm. For example, let's do Latin hypercube now. So we just select Latin hypercube. We have to specify how many samples we want to do. And if we press next, we have additional information because Monte Carlo is a very basic algorithm. You just say how many samples you want to have, and that's it. When we do Latin hypercube, we have additional information that we have to say. So smooth means, as I said, Latin hypercube divide the input space in a lot of tiny hypercubes, as many as the number of samples you specified. With smooth, it means that you will generate a random sample inside this hypercube, while without smooth, we will just select one hypercube randomly and put the sample in the middle of this hypercube. And then you have various criteria because in Latin hypercube selects this hypercube in a random way that is not purely random, but can be done, for example, purely random by saying none, or you can select the next hypercube so that you reduce the correlation with the points, or you maximize the distance between the points. So these are different criteria of what you can do for your Latin hypercube. And a maximum iteration is because if you do some additional conditions, it's kind of optimization to like reduce the correlation or to maximize the distance, and it will need to limit to do some iterations in order to achieve this optimum. And you can 5 iteration is okay to have a rough and fast argument, but you can, if you want to be more precise and more going towards the maximum distance, for example, with a point, you can increase to 15, 20, and so on. Let's keep like this, and then we press finish. And if we go looking at the results, let's have a look, for example, at the scatter plot to see if it looks different. Well, it looks very similar, but actually, in this case, in this case, you cannot really see much difference because we only have 4 random variables, so it's not very high dimensional. But if you would have like 10 or 20 random variables, it would have covered the input space in a much better way. I don't know. Sobol and Halton sampling are just similar. You just specify some additional input quantities, and it will generate a quasi-random sequence. I think that this is enough for it, and we can move towards the reliability.